Okay, welcome everyone. Thank you, Raimundo, for giving this another try on a Tuesday. I really appreciate it. And Raimundo is going to be talking about the Borcherds identity in logarithmic coordinates. Feel free to start whenever you're ready.
Thank you very much for the invitation. I apologize for the mix-up on Thursday. I should have checked that day instead of the few days before. So what happens here? Okay, good. So yeah, so I figured this crowd should be the only crowd where I can actually give this kind of a talk. I'm not going to give you any sort of a new idea nor anything fancy, and I'm just going to give a very technical talk, but it's something that I like quite a bit. So I want to start with the way that I start all my talks, which is what are conformal blocks on an elliptic curve. And this time I won't even mention, I think, higher Kähler homologies. Just conformal blocks is already good enough, and Jou's paper is already good enough. So you start with V, which is your vertex algebra. You start with, let me define X to be an elliptic curve. So this guy is just going to be C divided by Z plus Z tau. Or we're going to see this also as C star divided by Z. Here, the action of Z is n goes by multiplication by q to the n, and the isomorphism between these two uses an exponential change of coordinates. Q is e to the 2 pi I tau. Here, tau is in the upper half plane. So let me define gamma 1 to be sections of on X minus the mark point, and the mark point is going to be either 0 here, the image of 0 here, or the image of 1 here that get identified by this by some exponential map. So let me call these 2 points. I'm just going to denote them X, which is the mark point on the elliptic curve, and look at holomorphic functions that are allowed to have poles at that mark point. So that's going to be my gamma 1. And write this complex, which is gamma 1 tensor V in degree 1. This is my differential that decreases degree to V. And the map is, if you give me a function and you give me 2 vectors, you just do the only thing that you can do, which is take your function, apply one vector to the other vector, and take the residue of that, take an integral of that. And covariance by definition is the zero homology of this complex. So this is in degree 0. So covariance, variance is by definition the homology in degree 0, which is V divided by the image of the differential. And conformal blocks is the dual of that vector space. Or if you want vacuum conformal blocks or 1-point conformal blocks on the torus, comes with many names. Actually, this name is not the name that Jou gives. Jou calls conformal blocks something different. I might mention this in a bit, but this is already good enough. And this is, I think, what people call now conformal blocks, is the dual vector space. So this consists of guys in the dual, such that phi of anything in the image of G is equal to 0. Oops. But let's look at what is this differential concretely. Yeah. So concretely, this differential goes as follows. The space gamma 1 consists of constant functions, or you have one function that has a pole of order 2. I'm going to call this the Weierstrass P function. And then the derivatives of that function. You have one function with a pole of order 3, and so forth. So for each, this is the end derivative of this function, and so forth. So that's an explicit description of that space of functions. And well, the differential of the constant function 1, tensor A, tensor B, this goes to the residue of A of t, B. And on vertex algebras, this has a name. This is the zeroth product of A with B. If you do this for the Weierstrass P function, you're going to get something that I'll define it. We'll see what the form of that product is explicitly, but I'm just going to define it to be, to give it a name, just Weierstrass P of t, AT, B. I'm going to call this a PB. And in general, since the residue of a total derivative is 0, then the derivative of a function tensor A tensor B is the same as minus the differential of F tensor the derivative of A tensor B. This is the derivation of B.
Maybe you said this already. What are the super indices in P? What's P1, Pn?
These are the derivatives. So,
gotcha.
So you have the Weierstrass P function. The derivative is a function that has a pole of order 3. The derivative of the nth derivative has a function of is a pole of order n minus 2. So the point of this is that you can trade derivatives on your function by a derivative on the vector on the vertex algebra. So if you killed already elements of this form and you killed already elements of this form, then you kill everything else. So the space of conformal blocks is very explicit. A conformal block, definition, a conformal block on the torus is a linear functional V star such that these two equations are satisfied. Phi of A0B is equal to phi of A PB, and this is equal to 0. Let me just go back. Okay. So that's a very explicit description of what the space of conformal. Well, it's not an explicit description. It's an explicit definition of what is the space of conformal blocks is on the torus. And the question is, well, how many of those are, or how to describe them, and so forth. And we typically start talks by saying, well, Joux's theorem says that under some conditions, there's a theorem, the important theorem of Joux, is that under some finiteness condition and some semi-simplicity conditions, if V is C2 cofinite and rational, then traces on modules are conformal blocks. Then traces on irreducible modules, three modules, not only are conformal blocks, but they form a basis of the space of conformal blocks. So typically, what we would say is something along these lines, is that you have a module, a V module, and I want to define what is traces on this M, and would say something along these lines, that you grab your vector A in V and you send it to phi of A, which is the trace on M of A of t q to the L naught. This comes from the conformal structure of V. That didn't play any role before. And this is clearly wrong. This cannot be true as stated, for a number of reasons. One of them, there's this t here, and this side does not depend on t. And well, there's two corrections that we can make. We're going to make one immediately, and then there's other one that you might be used to, that here you correct this by the central charge. You put this minus c over 24. But today I want to understand this correction on t. So the fact that this fails to be a conformal block and then we need to correct this by multiplying by a power of t is what to me makes it interesting. And this whole talk in my mind comes because of something that bugs me of this whole theory, which is the fact that both in Jou's papers and in our papers, we use an explicit description of what this Weierstrass P function is, even though the description doesn't matter at all. So at some point we use analysis, and I would like to have proofs of either Jou's theorem or our theorems without using what the Weierstrass P function is. So let me describe what's going on. And actually, what is the issue that is happening here? Okay, so why this cannot be a linear functional? Why this this does depend on t is that your field for your vertex algebra is of the form an t to the minus delta minus n when a is primary conformal weight when a is primary of conformal weight delta, you write it like this, and then an increases or decreases. Eigenvalue of I naught of L naught by n. So your module becomes a graded module, and these guys are graded operators, and L naught acts diagonally, but these ANs do not act diagonally. They move the eigenvalue of I naught by n. So if you're taking a trace, the only thing that can actually help here are those modes that have n is equal to 0. So you see on the nose that you need to multiply by t to the delta if you want to have something that doesn't depend on t. So the first correction to t, first correction to phi is that you will want to use something like a trace on m of t to the delta a of t q to the L naught. Once you do this, then you kill this minus delta that is here. The only thing that survives is I naught. That is the only thing that contributes to the trace. And then this thing has a chance, at least, of being a linear function. Now, of course, most of the complication in Jou's paper is to prove that this is an actual complex number. As written here, this phi of a, now we know that it is some power series in Q. It's some power series in Q, and there's probably some rational power in the end. That's a correction that we're going to add eventually. It doesn't matter. It's just some rational number that is the lowest energy, but you have a power series in Q, not a complex number, and we want a complex number. So, and this is where the problem lies, is proof that this series is convergent. So that's hard, that's not trivial. Prove that this series converges. Okay. But even if you do prove that this series converges, I would want to prove that it is a conformal block. So I want to prove that this actually is a conformal block. So how do we prove? So want to prove that phi actually kills elements of this form, kills the residue at t of f of t, a of t, b. So we want to kill these guys. And how do we go? Let's suppose that this series converges and that everything is well defined. Okay, so the technique is always the same. Let's suppose that the series is a convergent series and there are no analytical problems. So you want to compute this. You want to compute the trace on M of a residue f of t, a of t, b. This is the vector. So now you apply this guy to another coordinate, let's say s, and then you put q to the L naught. That's the definition. And then probably here we need to make a correction by multiplying by s to the minus of s2 some delta, where delta is now going to be the conformal weight of these guys. So that's some correction that is irrelevant. It's just the correction that we just added here. So modulo that correction, you want to compute something like this. You want the trace of the field associated to a residue. And here is where Borcherds identity comes from, and I'm going to start my talk right now. So I guess I should have started here with defining what a vertex algebra is. Definition: a vertex algebra is a vector space V with an operation V tensor V Laurent series. Let's use this coordinate z, that I'm sure I'm not going to get it wrong, which grabs A tensor B and it sends it to A z of P, and subject to only one axiom. This axiom is Borcherds' identity and says the following. It says that for every function f of z and w that is allowed to have, so take it to be a Laurent series, a Taylor series if you wish, on z and w, but allow it poles at z is equal to 0, at w is equal to 0, or at z, z minus w, or at z is equal to w. So graph, this is just going to be a function that we're going to use as a test case. In fact, well, the axiom says the following, says that if you grab A of z, B of w, and apply C, I'm going to probably need to make this smaller eventually, so let's just move this thing anyways. So I'm going to multiply here by f of zw. It wasn't small enough. Let's move it again. And so I'm going to integrate out w. So this is just the coefficient of w to the -1, and then integrate z. And this is the same thing. So if you do this in the other order, the residue, and then another residue of f of zw, but now you put b of w first, a of z, c. So now you integrate first z and then w, and this turns out to be a residue, again a double integral, but now is a of z minus w applied to b, and then this thing applied to c. And the residues are, you first integrate, look at the coefficient of z minus w inverse, and then here you look at the coefficient of w inverse. So here there's something to be said, that is, how do you expand? In here there's no expansions that are taken, you're expanding in w inverse and z inverse, you're taking those coefficients. But here it means that whenever you see Z, you write it as Z minus W plus W, and you expand in the domain where W is bigger than Z minus W. Actually, when W is smaller than Z minus W. So this is Borcherds' identity. And why this is relevant to the above discussion is that it looks like we want to take a trace of this sub. We're applying a field A to B, and we're taking the field of that guy. So forget about C here. This identity is still true if I get rid of C's. And it's even still true if I get rid of C and I get rid of one of the integrations. So it's an identity of operators. So what Borcherds' identity is telling me is that if I used it, then I can replace this field A of B, A of applied to T, A of T of applied to B by this difference of these two fields. So then by Borcherds' identity, and I'm waving my hands, but I'll do this precisely in a bit. Oops, where do I? So by Borcherds' identity, this is the object that I want to compute, the trace of the residue F of T, A of T, B, S, Q to the N naught. And this is going to become a difference of two things. And well, here, yes? Oh no, there was another question. So here I have A of T, and then T should be Z minus W. So I'm going to replace it by that. I'm going to call this T Z minus W. This S is going to be W, so that it looks just like Borcherds' identity. And then this F was an elliptic function that had only one pole at Z minus W. So it's still just a function of Z and W. So that's fine. So by Borcherds' identity, I would expect this to be something like the trace at M. It's just that now I have only one residue, which is this residue, and I'm not taking this extra residue at W. So modulo that subtlety, I'd expect two residues. I'll expect to still keep a residue, but I will have F of Z minus W, A of Z, B of W, Q to the L naught, and then minus trace at M, the residue of F of Z minus W. And where are we? B of W, A of Z, Q to the L naught. So that's the first step. You use Borcherds' identity and you converted your condition of being a conformal block into this difference of these two guys. The second step is to use. I mean, if this is a trace and this was convergent, then the trace of A times B is the same as the trace of B times A. So here, this whole thing is residue of Z on both sides, actually. So the residue commutes with taking traces. You can just move this residue on the other side, and then the residue of A times this. I'm gonna take this term. I'm gonna look at the trace at M of a residue at Z of F of Z minus W, B of W, Q to the L naught, A of Z. And well, now you commute. So this was just because the trace is a symmetric function. So now you commute this guy past this guy, and you want to compare it with that. And when you commute Q to the L naught with A of Z, you realize that you have an equation that looks like Q to the L naught times A of Z. This looks like A of Q times Z, Q to the L naught. And then here you're going to pick up some conformal weight of A that appears there. So again, so you commute this guy here. So then the residual Z of F of Z minus W, B of W, A of Z, q to the L, a of q times z, q to the L naught. And then there's some power of q that goes out. That power of q is going to be completely irrelevant now, but you see that it looks like the term on the other side. It's just that now here this is q times z, not z. So I cannot really cancel that term. I would want this to be equal to minus this. So I would want these two terms to cancel each other because I want this to be a conformal block. And this isn't, because I have this q here. And I'm taking this residue at z, so in principle, what I could do is convert z, make the change of variables of sending z to z times q inverse. And the problem of that is that if I do that, then this f that was of z minus w is not invariant by that change. F is invariant by the change z goes to z plus 2 pi I tau. It's not invariant by the change z goes to z plus q. So it seems that these two coordinates are playing a different role. This elliptic function should be evaluated not in the exponential coordinates, it should be evaluated in the logarithmic coordinates, and the arguments to the vertex operator should be evaluated in the exponential coordinates. And this is something that that is there in Joule. Of course, I mean, you prove this theorem, but it's hidden as to why. Where does it come from? And you see it immediately here. So as soon as we fix this, we can make our function be elliptic. It's just that instead of using the coordinate z, I'm going to use the logarithm of that, so that it's invariant by these changes. Or the opposite. I could use for the vertex operators the logarithm, so that when I commute by q to the L naught, then I'm changing my coordinates by this change. The whole point is that vertex operators and the elliptic functions appearing should be on different coordinates. And this is something that is worrisome. This is something that, well, it is what it is, and that's how we're going to fix it. And this is the final answer to actual Joule's theorem. So Joule's theorem is theorem. And this is going to be, well, it's not the final answer, but it's almost the final answer, is that what is actually a conformal block is the trace at m of y to the e to the 2 pi I. This is not going to fit properly. 2 pi I z L naught. Let me use here. Yeah, okay. So z L naught of a e to the 2 pi I z q to the 2 pi I tau, or oh, sorry, q to the L naught, which is the same thing. Let me use 2 pi i's everywhere. E to the 2 pi I tau L naught. There's a correction of c to the over 24. This correction is irrelevant. This has to do with satisfying a particular differential equation. Has nothing to do with healing or not the images of the differential. So these are the guys. These form a basis for conformal blocks of V. But not really V. There's a different V. Let me tell you what that V is. If you have any algebraic structure with a product and you have an automorphism of vector spaces, suppose that you have some automorphism of vector spaces of that vertex algebra, then you have a new vertex algebra structure, where you just intertwine the multiplication by this automorphism. So you define a new vertex algebra structure where you grab A times B. If you want to multiply them, what you do is you apply this first. And now you multiply these guys. And now you map it back by R. So this is a new vertex algebra structure. So the vertex operator is very nasty here. So the vertex operator associated to A looks like R of R inverse of A of T R inverse. So this is the vertex operator A of T for this new vertex alpha structure on V. Of course, it's isomorphic. We're using R as an isomorphism of vertex alphas. It just turns out that when the vertex algebra V is conformal, then the whole group of automorphisms, so changes of coordinates of the ring of power series in one variable, acts on V. And the very explicit automorphism that is appearing here gives rise to an R that is very nice. So I'm going to take the automorphism, so it acts. So we have a representation, a map of now a morphism of groups from this automorphism ring to GLV. And in here, I have the automorphism that sends Z to e to the 2 pi I Z minus 1, actually over 2 pi I. So that's a very explicit automorphism. And that exponential change of coordinate gives me some R. I have no hope of describing what R is, but this expression here becomes very nice. So whatever this R is, R of R inverse of A of T R inverse is equal to e to the, well, actually, let me just not, because I always confuse these two. So I want to make sure that I actually get the right expression for this. So this is 2, because I got the normalizations wrong many times. 2 pi I T L naught of A evaluated in e to the 2 pi I T minus 1. Okay, so that's the new vertex operator structure. That's the observation of Zhu. That is fantastic. So he defines a new vertex operator structure where you use those vertex operators. Y of AT is equal to Y of e to the 2 pi I T L naught acting on A, e to the 2 pi I T minus 1. And well, those traces there, this is a vertex algebra structure that is isomorphic to V. The isomorphism is this R that corresponds to this change of coordinates, which is the exponential change of coordinates. And those traces are conformal blocks, not for V with the usual vertex operator structure, but for V with this vertex operator structure. And that's the full theorem of Zhu in the case where V is C2 cofinite and rational. Those traces are conformal blocks. They kill the image of the differential, but for this vertex alpha. And now I can go again for the proof. And then I realize that I need a new version of the Borcherds identity. So I'm going to do exactly, I'm going to go again over the proof that I just did. But now I'm going to notice that I'm taking traces on M. I'm going to take a trace on M again. So remember, what is the trace that I'm using? I'm using e to the 2 pi I T L naught A, and this guy evaluated in e to the 2 pi I T. And then I have this q to the L naught. So let's use Z to be e to the 2 pi I T. So this looks like the trace on M, and there's a residue here. No, there's no residue yet. Sorry. So this is the trace on M of A of Z z to the L naught of A, so z to the delta. Here's I of z, q to the L naught. So this is the first correction that we started with, that we needed to multiply by z to the delta. This comes from this change of coordinates. So that's the trace that we're looking at. But now, since I want to kill these operations, what I need to kill is something different. My complex now looks like v to v, and I give you a function of the coordinate t. So what I need to kill is the residue at t of the Weierstrass p function of t, y of a t b. Let me use this as a of t instead of, well, that's not going to be visible. Okay, so this vertex operator that I'm using here is not the original vertex operator. So this is what I need to kill. So if I go and apply the differential, I'm going to be trying to find a Borcherds identity that starts with the trace at n of the residue at t of the Weierstrass p function of t y of a t b. So that's what I want to kill. So I'm going to put here, this is my vector, but now I need to put it in this trace. So I need to write this guy in the coordinate z. I need to multiply this guy by z to some conformal weight of these guys. Well, the conformal weight of this is going to be the conformal weight of A plus the conformal weight of B. That's going to call it delta. And then I put here q to the L naught. And what I want is that this should be equal to two traces, one trace minus another trace on M of a residue. And now let's be careful, because what I want is to get expressions like what I had before. So here I want to have expressions of the form y of a z, y of bw, usual fields. Here, this is the modified vertex operator. These are the usual fields, q to the L naught, and here y of bw, y of az, q to the L naught. These are the usual guys. And here my function p should be a function of z and w. And here my function p should be a function of z and w. So that's the kind of Borcherds identity that I need in order to prove that theorem. So now let me tell you what is the Borcherds identity that holds and prove that identity. Okay? But at least this was, I think this was 40 minutes of motivations as to why I need a Borcherds identity of this form. And I can tell you a little bit more as to why I needed a stronger Borcherds identity than this, but let me just enunciate the theorem because that's what it is. So the first thing I'll do is, since this expression appears all the time, so we were correcting our field y of a z, we were actually using z to the conformal weight of a times y of a z. Let me directly work with those modified vertex operators. This is a definition. X of a z is going to be z inverse times y of z to the L naught of a z. So that has an extra z inverse that's going to become useful. But this is z to the delta times a times y of a z. So that's this guy. And I'm just multiplying it by z inverse. And the reason I'm using this is that now the expansion in powers of z is a n z to the minus n minus 1. And now these ANs are the ones that are graded in the module. These are the guys that raise or decrease energy by n. The important thing is that these vertex operators x of a z carry the information of the original vertex operators. They don't have this exponential change of coordinates embedded into them. So this, I'm going to call them modified vertex operators. They satisfy a useful identity that q to the L naught. So when you commute this guy, this doesn't pick up a q to the power conformal weight of a. So this is simply q times x to the a qz q to the L naught. So that's one identity double need. Okay, so the second ingredient that I want in my Borcherds identity, because the Borcherds identity that I needs to work with this elliptic function, this Borcherds p function, in both coordinates, in the coordinate t and in the coordinate e to the 2 pi I t, this coordinate z. Okay. So let's suppose that you have a function f that f is going to be, I want something slightly more general than elliptic, so I'm gonna tell you what it is. It's going to be a meromorphic function, on C that may have poles at the lattice m plus n tau. Tau is in the upper half plane. And it's either regular or at those points, or it satisfies that it is f of t plus m plus, well, t plus 1 is equal to f of t. So it's periodic, it's a function in the cylinder, but it's not periodic, not necessarily periodic with respect to tau. F of t plus tau is equal to f of t minus a constant alpha. And alpha is just a complex number. So this is quasi-periodic. These are the functions that I'm going to be allowing. If alpha is equal to 0, this is just the same as before. Alpha is equal to 0, this is just the Borcherds p function, the derivative of the Borcherds p function, and so forth. By putting this alpha being non-zero, I'm allowing an integral of this Borcherds p function, that is the Borcherds zeta function, that satisfies the equation d by dt of zeta of t is equal to minus the Borcherds p function. So by adding this quasi-periodicity, I'm adding one function, which is the integral of the Borcherds p function. And I'm adding this only because I know how to prove this theorem in this case, but it's fine. We only need it for what I'm talking today. I only need it for the Borcherds p function. So at the case, a periodic function, an elliptic function. The point is that whenever you have this function with these conditions and it's periodic with respect to t, then it has Fourier expansions. So it has Fourier expansions. So let me call those Fourier expansions f. Well, now you need to pick where. So this is the plane. Let's put our tau here. Let's put our 0 here. And let's say I'm looking for, this is where I may have a pole. This is where I may have a pole. And at 1, I may have a pole. So this is my lattice. I may have poles in these points. So if I am here, I know that I'm going to have a good Fourier expansion in this area, okay, at least inside of here. And I know that I'm going to have a good Fourier expansion below here. So let's call this guy f plus and this guy f minus. These are the Fourier expansion of my function of t. So that function has these Fourier expansions f plus of z is equal to f of t, meaning that if I put z is equal to e to the 2 pi I t, then in the domain where t, the imaginary part of t, well, this guy, in this domain plus is less than the imaginary part of tau, we can assume this, and it's bigger than 0, this equation satisfies. So this is a Fourier, this is a sum, this guy is a sum of f plus n, z to the n and this n is over the whole integers. This is not the kind of sums that we're used to in vertex algebras where we allow Laurent series. So this is over the whole integers, this Fn. So that's this f plus of z, and this is a convergent series in the usual sense, in the usual analytic sense, to f of t. And then we have another one, which is f minus, that satisfies the same equation, but in the other domain. So this is all subject to this identity. So explicitly, you compute those coefficients, f plus or minus sub n. By definition, this is an integral from t0 to t0 plus 1, f of t e to the minus 2 pi I n t by dt, where this path here is if t0 is just some element here, you just add 1 and you just go horizontally in the plus domain or in the minus domain, and they converge to this, those integrals give you these coefficients. So that's how you compute this Fourier expansion. Okay, and the theorem is this theorem, which I think we posted it with, this is Van Ekeren, Heluani, and this is, we posted it earlier this year, but I think I've given talks about this theorem for like 5 years already. Well, mentioning this theorem, but not focusing on the theorem. So what is this theorem? This theorem says the following. Okay, so, well, it's precisely what the Borcherds identity in this case is 2 pi I times x of the residue at t of f of t. And here I'm going to use y of a t b. So again, I'm using coordinates t for the function, for the elliptic function, and I'm using this modified vertex operator for this residue that I'm taking. So remember, this y of a t is Jou's vertex operator. Is e to the 2 pi I L naught t of a, and then the usual vertex operator here, e to the 2 pi I t minus 1. So that's this. And this thing here on the left, on the right hand side has the Fourier expansions of these guys. So it has the Fourier expansion on the minus domain of z over w now, x of a z, x of bw, minus the Fourier expansion on the plus hand side, zw, x of bw, x of az. So that's the theorem. I can tell you in a bit how do you prove this theorem. The proof is not so hard, but it takes a few pages of computations. And it uses the fact that you can compute these coefficients explicitly, and it uses the explicit form of the exchange of coordinates formula. But for me, the conceptual problem here is this Borcherds identity is adapted for elliptic functions in the sense that I only know how to prove it for functions that are quasi-periodic. I do not know how to prove this this identity for functions without using that condition. I have no clue if this is something that that is essential or not. This uses the fact that these particular integrals give the coefficient, so analysis plays an explicit role in this identity. But once you're giving me this as a black box, as an identity, which is a formal identity that doesn't care about anything, these are just formal power series on this side, you do not need at all ever the form of f. Just you need to only know that this series is the Fourier expansion of f. Then you can prove Jou's theorem. So let's prove that the trace, as we know it, is a conformal block. So what is the conformal block? We're defining phi of a now to be the trace at n of, well, I needed to kill z because x of az was not x to the z to the delta, but actually was z to the delta minus 1. So I need to multiply back that z that I added of xz q to the L naught. So this is phi of a, and I need to check that this guy kills the residue at t of some elliptic function f of t y of a t b, that this is 0. And now I use explicitly this theorem, because that's the trace at m of z of x of that. So I need to do the residue. Well, let's do that. So I need to do z times x of that residue of t, f of t, y of a t b, q to the L naught. Now I just use that theorem and say this is the trace at m of the residue at z, and then I have this z times f minus of z over w x a z x bw q to the L naught, and then I have, oh, this is f minus the trace residue at z, z f plus zw x bw x a z q to the L naught. And now actually is formal the change of coordinates of the cyclic permutations on inside of a trace. We pass this guy here. The trace of a times b is equal to the trace of b times a, and now we commute with q to the L naught using the equation that we had above. So this term, the first term here is the trace at m, the residue at z, z f minus z over w, x of bw, q to the L naught times x of a z, that this is the same thing as q times x of a qz, q to the L naught, and we solved our problem, because now this guy here is actually appearing with the same coordinates that it should appear here. This is a Fourier transform of my original elliptic function. So now you just make the change of coordinates. Z goes to z times q inverse. So when z goes to z times q inverse, you can put a q inverse here. This gets a q inverse that kills this q, and this becomes z, and you're fine. And now the whole point is that this was the Fourier expansion of the function f of t convergent in this domain, in this f minus. When you multiply this by q inverse, this becomes convergent now in this domain, and it converges to the same function because the function was elliptic. So multiplying by q was invariant. That corresponds to t going to t plus 2 pi tau, plus tau. So that means that this guy converges to the same function that f plus converges on the same domain. So this guy is equal to f plus of z over w. So now this is formally the same series. So this series as a series is 0. And I don't care about convergence. So I only cared about convergence to prove the theorem, but I don't care about convergence of the actual trace, which is the hard part of the Jou's. And this is actually what Jou does in a hidden way. So I actually suspect that Jou actually had our theorem. It's just that he didn't care about our actual theorem because he only cared about killing the Weierstrass P function. We need arbitrary elliptic functions in n variables, not only 2, because we care about chiral homology, not just conformal blocks. Okay, so I have a little bit less than 5 minutes, so probably I won't tell you how to prove it. So that let me at least tell you, indicate what would enter the proof of such a theorem, because it's not only computational. You need to realize that there's something conceptual going on. So let's say that I want to let's start with this expression, and I want to analyze what is this residue that I have here. Then here the exponential change of coordinates is already embedded because this was the definition of this deformed operation. So when I go and I say, well, let's try to analyze that, then I need to analyze this residue of t of f of t, y of a t b. And then I'm going to take a vertex operator of that later on. But the point is that this is equal to the residue of t, f of t, e to the 2 pi I. And now this is the conformal weight of a, y of a, e to the 2 pi I t minus 1 applied to b. And I need to integrate this with respect to t. So let me write this as dt, and that's what I need to integrate. But now this formally is the residue of t, f of t, e to the 2 pi I delta of a. There's a t here, of course. And then I have here an infinite sum, where I have an e to the 2 pi I t minus 1 to the n, and then I have here a y and b dt. So I see immediately that that this thing here, this f here is analytic, and it may have at most a pole at t is equal to 0. So this residue is an integral. This is the point where this was a formal power series, and at all times we're doing vertex algebra after all. But here I need to use the fact that f is analytic, and since this is analytic, this is an integral. There's an 1 over 2 pi I, but that's why the 2 pi I appears also in the theorem. But the whole point is that this is an actual integral. E to the 2 pi I t, the conformal weight of a, and then here there's an e to the 2 pi I t minus 1 to the minus n minus 1. Well, let's say to the n, it doesn't matter. Then I have this a n b, and then I need to sum. And now you do this case by case. So when n is negative, you just expand this guy, and you see explicitly the Fourier expansion of f. So expanding that power to the 2 pi I minus n. Well, it doesn't matter. Even for n, it's full equal to positive in powers of 2 minutes. E to the 2 pi I k t. You see the coefficients. You see the Fourier coefficients. Coefficients of f. So that's why, because you have the actual integral that gives you the Fourier coefficients of f. And then you use the usual Borcherds identity for the usual vertex operators to compare it with the other side. Once you compare, you transform these coefficients of f, this f in these coordinates to Fourier coefficients in the other coordinates, and then you just use the usual Borcherds identity to write them as products in the other way. All right, so I'll stop around here. That's a sort of theorem.